In 2024, interacting with AI required a user to provide a specific prompt and wait for a single output. Today, that linear interaction has been replaced by agents that receive an end goal and independently determine every intermediate step required to reach it. These digital workers operate without the need for constant human intervention, executing multi-step objectives by self-generating their own instructions. This shift towards autonomous action is projected by Goldman Sachs to add $7 trillion to global GDP over the next 10 years. We see the scale of this capability in the deployment of Cognition AI's Devon at Rakuten. Tasked with navigating a 12.5 million-line codebase, the agent completed its engineering objective in 7 hours with 99.9% accuracy. Beyond software engineering, Coca-Cola Africa has integrated these agents into their physical supply chains, automating fulfillment cycles to save planners an hour and a half of manual data management every day. The primary driver of enterprise value is now the ability to execute continuous, autonomous work across a network. Despite these technical milestones, 42% of enterprise AI projects currently report a return on investment of exactly 0. Many organizations are hitting a wall because they are attempting to run autonomous agents on top of data pipelines originally built for static chatbots. This index from the June 2026 AI Trends Report outlines the current state of the industry. To understand why so many deployments are failing to generate value, we have to examine the architecture of the agents themselves and the specific production challenges listed here. We need to explain why highly advanced models are leading to net negative productivity in nearly half of all corporate implementations. Recovering that ROI requires us to deconstruct the logic engine of a functional digital worker before we can isolate its failure modes. The internal logic of a 2026 agent is built on a continuous cognitive loop: plan, act, observe, and adapt. During the plan phase, the agent receives a final objective and reverse engineers the specific sequence of subtasks required to achieve it. In the act phase, the agent triggers external tools, query databases, and reads local files to carry out those steps in the real world. The observe and adapt phases allow the agent to evaluate its own results. If a specific action fails, the system identifies the error and returns to the planning stage to generate a new path forward. This is how a code generation agent functions. It will write logic, attempt to run it, and if it fails, it will continuously rewrite the code until the internal tests are satisfied. This looping mechanism is a significant departure from 2024 models, which simply stopped processing after delivering a single, often incomplete, output. This makes an agent a deterministic engine that pursues an objective independently of human pacing. Complex enterprise workflows often exceed the context capacity of any single AI model working in isolation. This diagram illustrates the Model Context Protocol, or MCP. It serves as a secure bridge between AI agents and local development tools like VS Code and GitHub. There are now over 10,000 published MCP servers that allow agents to navigate web interfaces and read local data packets directly, bypassing the need for a human to provide manual context. When a task requires multiple types of expertise, the agent-to-agent, or A2A protocol, allows the workload to be split across several specialized models. For example, a lead planner agent might autonomously delegate a specialized subtask to a dedicated commerce or support agent, then integrate that specific result back into the main workflow. The power of a modern AI system is determined by the efficiency of these communication protocols, rather than just the raw intelligence of the base models. We can see the impact of this architecture when it is deployed into highly specialized fields like personalized medicine. In genomic variant interpretation, AI systems are currently analyzing the genetic profiles of 500,000 patients to identify disease risks with speeds impossible for human researchers. However, healthcare AI faces a legal roadblock. Raw, protected patient data cannot be moved to a centralized corporate server for training or analysis. This map shows the solution: Federated AI. In this architecture, analysis happens locally at individual hospital nodes, and only the resulting analytical weights are sent to a central model. Institutions can share the mathematical insights gained by their agents, while the raw patient data remains securely locked on local servers. While this addresses privacy, it does not resolve demographic bias. Because genomic databases are predominantly based on European ancestry, the NAACP has released a report demanding equity-first standards and mandatory bias audits for these models. This federated approach allows for the discovery of specialized medical insights without compromising digital sovereignty. The theoretical perfection of agentic workflows often breaks down during actual enterprise implementation. 70% of developers report significant difficulty integrating autonomous agents with their existing infrastructure. This friction is caused by overlaying autonomous agents onto outdated legacy data pipelines that were never designed for high-velocity execution. This chart compares the speed of AI generation against the time humans spend correcting its mistakes, a burden known as Workslop. When employees spend more time auditing low-quality outputs than they would have spent doing the work manually, the project's return on investment becomes negative. Many enterprises discover the strain too late because they failed to establish clear baseline metrics to track the actual cost of these human-led corrections. If an autonomous agent applies high-speed logic to flawed data, it only serves to automate the production of errors. Beyond productivity loss, the most immediate financial risk of 2026 is exponential, runaway token costs. This diagram shows a recursive loop. If an unmonitored agent expands its scope or enters a retry loop, it fractures into thousands of redundant nodes, spiking compute costs instantly. A single broken API call triggers an infinite cycle, depleting budgets in hours. Early adopters like Uber faced these issues directly when experimental agents generated massive, unforeseen operational bills. These financial risks have necessitated the development of agentic token control platforms. These are governance layers that enforce hard-coded limits on agent autonomy and provide real-time monitoring of every token spent during an execution loop. Sustaining ROI in the agentic economy depends on the development of these rigorous governance layers.